In lecture 3, we will discuss the remaining flip-flops that we need to discuss. First, in lecture 1, we already discussed D flip-flop. Now we will discuss the other flip-flops. They are known as SR, JK, and T flip-flop. And after completing the basic idea, we will also discuss the counter design by using this SR, JK, and T flip-flop in the next lecture. So we'll also discuss the logic symbol and the excitation table, truth table, and state diagram, and how we can find the output waveform, and also the standard ICs used to perform this function. And first we will start with edge triggered SR flip-flop. Okay. And we already discussed what do you mean by edge triggered and level triggered. So I'm not going to explain all these things in this particular lecture. So if you are not aware about this edge triggered flip-flops, so please watch lecture 1. Okay. And SR inputs of the SR flip-flops are called synchronous inputs because the output is changing with respect to the specific point of the clock signal. Okay. Or this S and R inputs are sensitive to the edges of the clock. Okay. Either rising edge or the falling edge. So the first one is indicated as a rising edge clock, and the second one is indicated as a falling edge clock. So the second flip-flops is known as the negative edge triggered flip-flop. So this is a positive edge triggered, and this is a negative edge triggered flip-flop. Okay. So, and the working of this SR flip-flop, normally this name SR indicating set and reset. Okay. And for set we will use S, and reset we will use Rlet. So set reset flip-flop. Okay. It mainly perform two functions, set function and reset function. Now we'll see the working of this SR flip-flop. Okay, we will take the example of positive edge triggered SR flip-flop, and this is a basic truth diagram of this SR flip-flop. And if you take the SR flip-flop, there can be the first possibility, SR inputs are 0, 0. Okay, two inputs lines, okay, S and R, and assume that initially the Q1 input is 0. Okay, Q1 input is 0. So after applying a clock pulse, okay, when there is a positive edge, inputs are sensitive, and there will be a change corresponds to that. So initially the Q1 is equal to 0 before applying the clock pulse, and after applying the clock pulse, the Qn plus 1, next state will be equal to 0. If it is 0, the next state will be equal to 0. Okay, that is indicated here. And SR inputs are 0, 0, and the present state of the system is 0. The next state is 0. For example, I will consider another case. Initial input 0, 0, and the Qn present state is 1, and after applying the clock pulse, Qn plus 1 will be equal to 1. Okay. So if SR inputs are 0, 0, the present state can be 1. Another possibility, the next state is exactly the same. So there is no change in the output. So we can call it as there is no change. Now we'll discuss another possibility, that is SR inputs are 0, 1. Okay, that 0, 1 is actually, you can indicate as S for set and R for reset. In this particular case, reset is equal to 1, so this line will be active. Okay, so he can see that here R is equal to 1 means if Q1 is equal to 0, then Q1 plus 1 output becomes reset. It's already 0, so there is no change. If it is reset means the output is 0. But we'll consider other possibility. If SR input is 0, 1 and Q1 output is equal to 1, then next state after applying the clock pulse, okay, the next state of the system will be 0 because the reset pin is high. So Qn plus 1 is equal to 0. So here you can see that there's a change from 1 to 0 because this reset signal is equal to 1. So it is very easy to remember the SR flip-flop truth table. When R is equal to 1, the output becomes 0. So that is known as a reset condition. Okay. And if SR inputs are 1, SR inputs are 0, 1 or R is equal to 1, then the next state will be 0 irrespective of the present state. Okay. And now we will discuss the 1-0 condition. So 1-0 condition means set is equal to 1. So if S is equal to 1, whatever be the present state, if it is 0 or 1, output becomes 1. So that is set condition. Okay. Qn if 0 or 1, the output is equal to 1. So that is not a set condition. Another important point regarding this SR flip-flops, this for the input S is equal to 1 and R is equal to 1, so we cannot predict the next state. Okay, so in SR flip-flop, this 1 and R inputs are considered as invalid inputs. So there will not be any input like S and R. So if S and R occurs, and if the Qn set is 0 or 1, we cannot predict, we cannot say the output value. It can be 0 or 1, so that we cannot conclude. So we'll consider the last case 1 1. SR is equal to 1 1, we'll consider as the invalid possibility. Okay, and due to this problem, this SR flip-flops are not that much common. So in order to solve this particular problem, we are using another flip-flop. They are known as JK. Okay. So instead of using SR, in most of the case, we are using JK flip-flops due to this particular problem. Okay. And so this is a very lengthy table. So in order to discuss, we will use a very small truth table. For example, and here you can see that the clock signals are indicated as rising edge. Similarly, you can indicate falling edge also. All the difference is that clock signal will indicate as low. And without representing the clock and all, in the simplified form, I can represent the truth table of SR clock like this. If SR 0 0, we know that if S and R are 0 0, we can say that there is no change in the state. 0 will continue in the same state, 1 will continue in the next state. So Qn plus 1 is equal to exactly Qn. Okay. Next state is equal to the present state. And when the input is 0 1, okay, that is reset condition, output is reset, so it becomes 0. Okay. And for other combination, for it is 1 0, okay, for 1 0 condition, the output is set, so you can write 1. And last case 1 1, it's invalid, so we'll write this. Okay, this is SR flip-flop truth. Now we can discuss the output of a particular waveform. Consider that the clock signal is applied here, and S input is here, and R input is here. So 2 3 waveforms are given. We need to find out the Q and Q bar output. And we know that this is the truth table of SR flip-flop, and we need to verify the rising edges of the clock because it's a positive edge triggered clock is indicated in SR flip-flops. So this is positive edge triggered. Now we need to assume that initially the Q output is 0. Okay. Now we need to verify the output. Here you can see that SR input are 0 0 at this particular point. If it is 0 0 at this particular point, means we'll consider as the output just before the clock is Qn. Now we need to find out Qn plus 1. So at this particular input, clock rising edge, S input is 0, R input is 0. So 0 0. If the condition is 0 0, it will continue Qn plus 1 is equal to exactly Qn. So Qn plus 1 means after applying the clock. So before applying the clock, Qn is 0 because it is given that assume that the positive edge flip-flop initially reset, means initial value of the Q is equal to 0. The initial value of the Q is equal to 0. After applying this clock pulse, SR inputs are 0 0. If SR inputs are 0 0, Qn plus 1 is exactly same as Qn. So you'll get 0 here. Okay. Similarly, if you continue like this, it will be 0, and next clock's input here the second. Here you can say SR inputs are 0, 1. 0, 1 means it's a reset condition. So again, whatever be the input, the next output will be 0. So this is a reset condition. So after Qn plus 1, at this particular instant, this is a Qn plus 1. After applying the clock pulse, it is 0. So it will continue like this. Okay. And when it reaches the third rising edge, here it is 1 and here it is 0. 1, 0. And for 1, 0, it is a set condition. So Qn plus 1. After applying the clock pulse, it becomes 1. So Qn plus 1 is equal to 1. So the output changes from 0 to 1. And it will continue like this. And now we can see that here it is 0, 1. So before here it is 0, 1 means again it's a reset condition. Okay, the output becomes 0. So Qn plus 1 should be equal to 0. So the output changes from 1 to 0. And now we can see that this is 1, 0, fifth clock pulse. 1, 0 means is again a set condition. So again output changes from 0 to 1. So Qn plus 1 is equal to 1 here. So there is a change from 0 to 1. And here you can see that again 1, 0. 1, 0 means again set condition. So Qn plus 1 will be equal to 1 after this point. So this will be the output. And Q bar, this is Q actually. So Q bar is just opposite of this. So we can draw just an inverse waveform of the Q. Okay. So when it is 0, it becomes 1. So here it is 1, it is 1, here it is 0, 1, 0. So this is the output of the SR flip. Now we can discuss the excitation table of the SR flip flop. SR flip flop truth table we already discussed. By using this flip flop, we can truth table. I can write the excitation table. Excitation table shows that input that are necessary to generate a particular state when the current state is not. Means if you know the present state and next state, and we need to find out what should be the inputs. So for example, we know the Qn and Qn plus 1 state, and we need to identify what are the inputs for this particular state change. Okay. So this table state lists the required inputs for a given change of state. So in this particular state, the first you can see the Qn and next Qn plus 1. And in order to occur this particular state change, what should be the input? So first we need to fill 0, 0. And Qn is 0 and Qn plus 1 is 0. So if you look at this particular truth table, here you can see that there is a change from 0 to 0 for this particular condition, and another change occurs here. So in these two conditions, here you can see that there is SR inputs are 0, 0 and SR inputs are 0, 1. So two possibilities are there. Okay. When there is a change like this, Qn is equal to 0 and Qn plus 1 is equal to 0, 0, 0 occurs in two conditions. Here you can see that S is equal to 0 and R can be 0 or 1. Okay. So two possibilities you will get. S is equal to 0 and R is equal to 0. And when S is equal to 0 and R is equal to 1, we can expect a change from 0 to 0. Okay. Qn and Qn plus 1. So we can write the two states by using a single representation, that in both the cases S is equal to 0, but R can be any value. So I can conclude that when S is equal to 0, we can expect a change from 0 to 0. So we can write 0x. Okay. Similarly, now we need to verify the condition 0 to 1. When this 0 to 1 occurs. So 0 to 1 occurs, this is one possibility. This is only one possibility. So that state change occurs when SR inputs are 1, 0. So we can write 1, 0. Now we can consider another possibility, that is 1, 0. Okay. Qn and Qn plus 1 are 1, 0. So 1, 0 occurs. This is one possibility. This is only one possibility. For that, SR input should be 0, 1. So we can write it 0, 1. SR inputs are 0, 1. Now we need to check 1 1 condition. So 1 1 condition occurs. This is one possibility. This is another possibility. So SR input can be 0 0 or 1 0. So SR inputs are 0 0 and 1 0. So for the two possible inputs, the output is 1 1. Okay. So here you can see that R is equal to 0. S can be any value, 0 or 1. So you can put it like this. Don't care, 0. So X 0. Okay. This is the excitation table of SR flip-flop. Okay. Now we need to discuss about the state table and state diagram very specifically. So state table is also similar to that of your truth table. So present state SR input and what will be the next state. So we can consider all these quantities are the inputs and this is the output. Okay. So when the input is 0 and or rather so not input, Q1 is equal to 0 and you need to consider 4 possibilities 0 0 0 1 1 0 1 1. And similarly when Q1 is equal to 1, again you need to consider 4 possibilities 1 1. Okay. So you can see the table when the input is Q1 is 0 and S R is equal to 0 0 means it will continue in the Qn plus 1 will be exactly equal to Qn, so you can write 0. In 0 1 it's a reset condition, so again output is 0. For 1 0 condition it's a set condition and 1 1 is invalid condition, we don't know what will be the output. When the input is Qn is 1 and the SR inputs are 0 0, you can write Qn plus 1 is exactly same as Qn, so it will be same. Okay. When it is 0 1, it is a reset condition, so 0. When it is 1 0, set condition 1 and last is 1. So you will get the state table which is exactly same as your truth table. The only thing we need to write some specific order. Okay. So present state input and then next state. Now we can draw the state diagram. So state diagram means there can be two states. For the Q output, it can take two values. Q can equal to 0 or Q is equal to 1. And now assume that when Q is equal to 0, okay, this is Q is equal to 0 and your SR inputs are 0 0. If SR inputs are 0 0, okay, so the output is again 0. So SR inputs are 0 0. And another possibility, SR inputs are 0 1. For SR is equal to 0 0 or SR is equal to 0 1, the output is equal to same, Q is equal to 0. Now we need to check when SR inputs are 1 0. When SR inputs are 1 0, next state is 1. So Q becomes 1. So that's when SR inputs are 1 0, it will go to the next stage. Okay. And now we need to analyze this 1 1 condition. We don't want to analyze because this is an invalid condition. Now we need to check about one condition. Okay, now it's in the second state, Q is equal to 1 state, and in Q is equal to 1 state and SR inputs are 0 0, it will continue in the same state. So when SR inputs are 0 0, it will continue in the next state. Sorry, same state. And when it is 0 1, okay, it goes to Q0 state. That is Q is equal to 0 state. And presently it is in Q is equal to 1 state, and now the inputs are 0 1. So SR inputs are 0 1. It will go to the next state. Okay. Now the input condition is 1 0. If the input condition is 1 0, it will maintain the same state. If Qn is 1, Qn plus 1 is also equal to 1. So here you can put one more condition, that is 1 0. Okay, this is a, so we need to correct here. You need to write one more case, 1 0. So this is the excitation table, sorry, state diagram. And now we need to write the characteristic equation of this particular flip-flop. So in order to write the characteristic equation, it's very important for a flip-flop. And so characteristic equation means we need to write an equation for Qn plus 1. So we need to write Qn plus 1, this is the output in terms of Qn, S and R. So if you write S and R, so you need a K map, so which is indicating a 3 variable K map, Qn, S. So this is Qn and this is S and R. So we put it as Sn and Rn, that's all. So after indicating the values, you know that Qn plus is equal to 1 in 3 cases. So we are indicated that. And now we can set this is Qn and this is Rn bar, okay, or simply R bar. So this is equal to S and R. So you are getting two values, okay, Qn Rn bar and S and R bar. So this is the characteristic equation of SR flip-flop. So this is a practical IC which is used as a SR flip-flop. Okay, as a code, SR means within a single IC you will get 4 SR flip-flop. Okay, this is actually latch, not a flip-flop, means because it will work like a level triggered one, not edge triggered one. This is a level triggered. SR flip-flops are not much common because we are using JK flip-flop instead of that. That's why the SR flip-flop ICs are not much common. Okay. So now we'll discuss JK flip-flop. We already mentioned that similar to JK flip-flop. JK flip-flop is similar to SR flip-flop for the set, reset, and no change condition. But in the case of SR flip-flop, there is one invalid condition, that is 1 1. So in the case of JK flip-flop, there is a valid output for this 1 1 in. That's the only difference. So there is no invalid state in the case of JK flip-flop. That's the only difference. So two cases you can see that one is a positive edge triggered and another one is a negative edge triggered clock. Now we can discuss the truth table of JK flip-flop, which is exactly same as SR flip-flop. You can simply JK inputs are S and R. And one more point, and this JK flip-flops are named like this JK because it's the honor of Jack Kilby, who invented the integrated circuits. That's the letter J and K. So instead of S and R, we are using J and K letter. So the truth table is exactly same as SR flip-flop up to this point. Okay. So when the input is 0 0, you can say that it's a not change condition. But it is in 0 1, okay, 0 1, it is a reset condition. So and when it is 1 0, it's a set condition. Okay. You can simply talk about set and reset pins. And this is the final case when the inputs is 1 1, okay, and the present state is 0, next state will be 1. And when the input is SR inputs are JK inputs are 1 1, and the present state is 1, next state will be 0. So you can see that output is a complement, or we can call it as a toggle output. Okay. So now in the case of JK flip-flops, the last possibility is a valid one. 1 1 is equal to as a toggle case. So now we can simplify this SR flip-flop, not SR flip-flop, it's a JK flip-flop truth table like this. When the inputs is 0 0, it will continue Qn plus 1 is equal to Qn, and when it is 0 1, it's a, you can think about set and reset condition. So this reset is equal to 1, so output becomes 0. And in this particular case, set is equal to 1, so output becomes 1. And when there is 1 1 input, in the case of JK flip-flop, which is equal to Qn bar, okay, it will just complement the previous state. Now we can think about the output. So this is a truth table of JK flip-flop. This is a given waveform. You need to apply clock here, J here, and K here. So we can, one more point, this is a negative edge triggered clock. So we can find output. Negative edge triggered means we need to identify the output change only during the negative falling edges. So at this particular instant, J input is 1 and K input is equal to 1. Okay. So Qn initially reset condition. So initially the value is equal to 0. That is Qn is equal to 0. Now after applying this falling edge clock, and at that particular instant JK inputs are 1 1. If JK inputs are 1 1, next state Qn plus 1 is equal to Qn bar. So it becomes 1. Okay. Similarly, we need to evaluate each case. Now you can see that here qn is equal to 0 when the inputs are 1 1, qn plus 1 is equal to qn bar, so it is 1. Now at this particular instant you can see that this is 0 0. If it is 0 0, it will continue the previous edge. So at this particular instant qn is equal to 1 and qn plus 1. After applying the clock pulse, qn plus 1 is exactly qn, so you will get 1 again. So it will continue like this. During the third falling edge, the input is JK input is 0 1. If it is 0 1, it becomes reset. So in this particular case, qn is equal to 1 and qn plus 1. For 0 1, it is 0, so changing to reset condition. Now for the fourth falling edge, JK inputs is 1 0. If it is 1 0, it becomes set condition. So qn is equal to 0 here, but qn plus 1 is equal to 1, so it will change from 0 to 1. Now during the fifth falling edge, where it is 1 0, and it's 1 0 means again it's a set condition. So qn is equal to 1 and qn plus 1 is 1, so it will continue the same state. Okay, so when it is 1 1, it is JK inputs are 1 1, it's a toggle. When JK inputs are 0 0, no change. When JK inputs are 0 1, it's a reset condition. This is 1 0, JK inputs are 1 0, again JK inputs are 1 0. Okay. Now we can discuss the excitation table of JK flip flop. Okay, and it's not it's a JK flip flop. Here also this is not SR, it's a JK flip flop. Now we can see that first we need to identify 0 0 change. Okay, excitation table means present state and next state, and for the corresponding state change, what should be the input condition. Okay, you can see that 0 0 change occurs. This is one possibility, this is another possibility. So we can identify two JK values are like this: 0 0 0 1. So you can write respective of k, when j is equal to 0, you can expect a change from 0 to 0. So you can write 0x. Okay, j can take value 0 or 1, so we can put it as a down care condition. And similarly, the other possibility we need to take, it's 1 0. Okay, when there is a change from 0 to 1, sorry, 0 to 1. 0 to 1 occurs, this is one possibility, this is another possibility. So we can write JK input is 1 0 or JK input is 1 1. We can expect a change from 0 to 1. So here you can see that J input is 1 always and K input can be 0 or 1. So you can write 1 down care. Okay, because J input is 1 in both cases and K is 0 and 1. So K, we can put it as a down care condition. Similarly, you can try the other one. When the JK input is 1 0. So you can look at here, this is 1 0 change and this is another possibility. So you'll get two cases, 0 1 and 1 1. So you can see that K input is constant in this particular possibility 1 and J input is 0 1. So you can put J is equal to down care condition and K is equal to 1. Now the last case 1 1. 1 1 occurs, this is one possibility and this is another possibility. In this particular case, 1 1 occurs when JK inputs are 0 0 and JK input is 1 0. So you can see that in both the cases K input is 0. Okay, J input can be 0 or 1. So you can put X here. So this is the excitation table of JK flip flop. Now this is a most popular JK flip flop IC that we are using. It's 7473. Okay, 7473 contain two JK flip flops. Okay, here you can see the different inputs: clock signal, clear signal, K1 input. Okay, and here J1 input, Q1 bar, sorry, Q1 and Q1 bar, and this is a ground and VCC. Similarly, you can see other clock, clock 2, clear 2 pin, and J2, K2, Q2, Q2 bar. Okay, so the clear and preset inputs we already discussed in lecture 1. So please watch lecture 1. Okay, to know the direct input signal. Okay. And now the other ICs which are commonly used, 7473 is a dual JK flip flop with clear input. So if you apply any uh, signal in that particular point, clear signal is equal to, if you apply clear signal, the Q output becomes 0. Okay, it's an asynchronous input that we already discussed in lecture 1. And 7476 IC contain dual JK flip flop with a preset and clear, and 107 contain dual JK flip flops with clear only, and 4027 is a CMOS IC. Okay. Most commonly used one is 747. Okay, now we need to discuss again. It's not SR, it's a JK flip flop state table and state diagram. Again, there's a mistake. JK flip flop. Okay, this is the state table. Okay, just like your truth table itself. So 0 and 4 possibilities. So if present state is 0 and JK inputs are 0, 0, 0, 1, 1, 0, 1, 1. Okay. So if it is JK inputs are 0, the output Qn plus 1 state will be 0. Here it is 0, here it is 1, and it is 1. So it is written here. Similarly, for possibilities 0, 1, 1, 0, 1, 1. It will 1, and here it is 0, 1, and it's 0. Okay. By using the truth table, you can fill the state table also. And now we need to write the state diagram. Okay. In state diagram, we can see that it's not D flip flop. So please correct it. It's a JK flip flop. Okay, here also. Assume that Q input is 0. And if Q input is 0 and JK inputs are 0, 0. JK inputs are 0, 0. The next state is exactly C. So we can see that the transition again going back to the same state. And when it is 0 and the JK input is 0, 1. JK input is 0, 1. Okay, it goes to 0 state again. And when the present state is 0 and JK input is 1, 0, it goes to next state, that is 1. So when the JK input is 1, 0, it's again go into the Q is equal to 1 state. And when Q is equal to 0 and JK inputs are 1, 1, it goes to the next state. So you need to write one more possibility. But here we need to add one more case in the case of JK flip flop. That is, we need to consider this case also. Okay, when JK inputs are 0, 1, you are getting exactly the same. Okay, when the present state is 0 and JK input is 0, 1, it will again maintain the 0 state. And now we can consider the other state 1. When Q is equal to 1, Q is equal to 1, and JK inputs are 0, 0, JK inputs are 0, 0, the next state is same, Q is equal. So we can see again going back to the same state, Q is equal to 1 state. When Q is equal to Qn is equal to 1 and in the 0, 1, it will go to the 0 state. Okay, so you can see here it is 0, 1. Now Q input is Q state is equal to 1 and the JK inputs are 1, 0, it will maintain the same state. So here you need to write one more possibility, that is 1, 0. Okay, and last 1, 1 state and going back to the 0 state. So now we need to write the characteristic equation of this particular flip flop. So for that we need to implement Qn plus 1. We need to design Qn plus 1 in terms of Qn and Jk. So here it is Jk bar, J bar, K bar. This is J bar, K, and this is Jk bar. Now by looking at this particular table, you can write your equation. This is Qn bar and Jn, and here if you group these two ones, you can write Qn and Kn bar. Okay. So this is a equation for characteristic equation for this particular JK flip flops, Qn plus 1. Now we'll discuss the fourth category. We already discussed D, SR, and JK flip-flops. This is again a simple edge-triggered flip-flop. It is known as a T flip-flop, or we can call it as a toggle flip-flop. So, okay, toggle flip-flop is a complementing flip-flop. Okay, we'll see. Again, there can be two possibility: positive edge-triggered or negative edge-triggered clock. Okay, and here you can see the truth table of this particular. Again, this is not D; it's T actually. For example, the T input is 0. Okay, the T input is 0, and there is a positive edge triggered clock, and the present state of this particular system initially 0. Then after applying the clock pulse, you are getting exactly the same thing. Qn plus 1 is equal to 0 itself. Okay. Now I can consider another possibility. The T input is 1 and Qn is equal to 1. Then Qn plus 1 state is also 1. Means there is no change. If it is 0, it's 0. If it is 1, 1. So this condition is known as 1. Now we'll consider other possibility. Okay. That is the T input is 1. When the T input is 1 and the Qn state is equal to 0, okay, and if you are applying a positive edge triggered clock, Qn changes to 1. So there is a toggle output. Another possibility, if Qn is equal to 1, then that 1 becomes 0. Okay, this happens only when T is equal to 1. When T is equal to 1 and there is a positive or negative edge triggered clock, the output toggle, or there is a complement output you will get. So this is a truth table. If T is equal to 0, there is Qn plus 1 exactly Qn, and when T is equal to 1, the next state is Qn. Now we can write the excitation table of T flip-flop. So these are the different possibility. That is a truth table, and now we need to write the excitation table of T. So then there is a change from 0 to 0. The T input is 0. So you can see that T input is 0. And when there is a change from 0 to 1, 0 to 1 occurs when T input is 1. So you can say that T input is 1. When there is a change from 1 to 0, 1 to 0, the T input is again 1. So T input is 1. When it is 1, 1, and 1, 1 occurs when T input is 0. So it's very simple to write. When there's a change in the state, the T input is 1. Otherwise, T input is 0. Now we can write the state diagram of this particular T flip-flop. Okay, it's exactly same as the truth table itself. The present state is 0 and T input is 0 means output is 0, and present state is 0 and T input is 1 means there is a toggle, so 0 will change to 1, and the present state is Qn is equal to 1 and T input is 0 means it will continue that state, so it is 1, and here you will get the toggle output. Okay. Now we need to write the state diagram. When Q is equal to 0 and T input is 0, so it will maintain the same state, Q is equal to 0, and when Q is equal to 0 and when T input is equal to 1 and Q is equal to 0, it will go to the next state. Okay, and when Q is equal to 1 and T input is 0, it will maintain in that particular state, and finally when Q is equal to 1 and T is equal to 1, it goes back to the other state. Okay, so now we need to write the characteristic equation. For writing the characteristic equation, we need to write Qn plus 1. Okay, Qn plus 1 is equal to 1 in two cases, so you can write this is one possibility and this is another possibility, so you can write Tn XOR Qn. Okay, an XOR gate. Now we can verify the output waveform of this particular T flip-flop. Assume that this is a positive edge triggered clock we are going to apply. Okay, and this is a truth table of T flip-flop. Now this is a T input given. Okay, we need to find the corresponding output. So we can verify this particular output. So here during the rising edge of the clock, the T input is 1. So T input is 1 means assume that Qn is 0 initially. So when the T input is 1, Qn plus 1 becomes the toggle output. So it will be Qn bar, so which is equal to 1. So that's why the output is 1 here. Next, during this particular rising edge, T input is 0. If T input is 0, Qn is 1 here. So Qn plus 1 is exactly Qn. So we'll get 1 again. So during the third clock, T input is 1. If T input is 1, Qn plus 1 is equal to Qn bar. So here it is 1. So it becomes 0. Now during the fourth rising edge, T input is 0. If T input is 0, Qn plus 1 exactly equal to Qn. So Qn is equal to 0 here. So it will continue that particular state. This is all about the flip-flops basic characteristics. So we already discussed D flip-flop, G flip-flop, SR, and JK. Okay. Most commonly we are using in D flip-flop and JK flip-flop, and by simply modifying this JK, you can write T flip-flop. So there is no that much T flip-flops ICs are not that much common. By simply modifying this JK, you can perform the function of T flip-flop. And SR flip-flop, there is some limitations, so we prefer JK. Okay.